See the screen? You can see the screen, right? Solve this question.
So,
You want to solve this question?
yes, sir.
Okay. Okay, this one. Background noise is there.
Wait, sir.
There are two straight wires. EOB and COD. See the other side.
For AOB, direction is reversed, no, sir. From A to B.
Does it matter? Hold on. So where is the point P? It's the distance D from O along the direction perpendicular to the plane containing the wires. So it's here then. It's on the z-axis sort of. So this is x-axis, this is y-axis, this is z-axis. The point D is here. Then. Right. So according to I1, the magnetic field direction will be towards x-axis, say P1, and this one will be towards minus z-axis. Doesn't matter because the angle between B1 and B2 is 90 degrees, and we just need the magnitude. Okay. So this formula is going to be Ampere's rule, right? E into 2 pi r equal to I1, where r is D. D1 is 1 by 2 is common. So
But it is not a closed loop, no, sir.
it's an infinite wire. too long. Yeah, that's what it said long. It should be say very long or infinite. Okay, otherwise it's not easy. Okay, only if it's infinite we can use amplitude. So magnitude will be B1 square plus B2 square. The common thing is 1 by 2 pi d square of I1 square plus I2 square. Check the answer.
It's the right answer.
Yeah, so the important thing is one it's infinite there, so you have this formula from amplitude. So magnetic field is 1 by 2 pi r into I. And first thing is to visualize where the point D is. Okay, the point D in a plane perpendicular to the plane containing the bias. Again, it's not clear. Okay, then it can be here also. The point here also it's around. So the simpler point is this one.
Okay.
So because if it is somewhere only if at this point on the z-axis, this distance from both the wires will be d. This distance. And
Yes, sir.
okay, this one. Okay, this is a standard question we already done.
Yes, sir. In this question I understood, sir. I forgot to delete that one.
Okay, so actually there won't be any force. The force due to these two will cancel.
Yes,
Right?
sir. Non-uniform force, but opposite.
This force is more and this force is less. So this force will dominate.
Yes, sir.
This looks similar. Conductance by side long straight line. It moves towards the right, constant velocity. This is constant velocity. Constant velocity means what does it mean? As soon as it is constant velocity, what does it mean?
Zero.
What is zero?
But it's not charged, no, sir.
No. Forget about everything. Internet is not proper. Okay. So once you say it's constant velocity, it means acceleration is zero, right?
Yes, sir.
Acceleration zero means what? Acceleration is same as force.
Yes, sir.
Force is just mass into acceleration. So force is just k division of acceleration. So force is zero. So force is zero. It's possible because from this question itself, there will be a net force, right? Because the force on this one is more. So it's possible for the force to act on this if there is a in addition to this there is a current. Here also there will be a current. And this force, the current is same. How can the force be zero? It's exactly the same question. What is self-induced? There is some current in this loop. The current in this loop is same. The force on these two will cancel out. Force into perpendicular wise is zero. Force into parallel.
Yes, sir. Force on top and bottom line will cancel each other.
So, so this force and this force, they will. So this force is more. What answer they are given?
B, sir. Second
So,
option.
yeah. So yeah, I think we can forget this constant. Okay, okay. Right. Okay, okay. This is a different thing. It's constant velocity by an external agent. Okay. An external agent is maintaining constant. Okay, we don't know bother. Okay, this is different from the previous one. Basically, you have to find the flux through this area. Okay, and d phi by dt you have to do. And the flux will change because it's moving.
That is electromagnetic induction chapter only, sir. Why
Yeah, yeah.
are they given?
So flux should it be okay, this thing. Yeah, yeah. See, the magnetic field here at a distance x. Okay, how do you find the magnetic field in this entire region? It's not uniform, right? It's a function of x.
Non-uniform.
Yeah. So at a given time, when it's a distance x, the total flux will be something, right? When it moves away, the flux will decrease because you're moving away from the source, right?
Yes, sir. Yes, sir.
So this flux will be this current. So just find as a function of x.
Mu naught I by 2 pi x. Magnetic field equal to.
First thing is, what is B at x? It's mu naught by 2 pi x into I, right? By amperage.
Yes, sir.
Okay. So so you have to find the flux here inside those two. There's integral dx dx. Because if we take a strip here at distance x of thickness dx, the flux is that will be this one, right? So this you have to integrate from x equal to this one. And I assume this is x naught. Okay. Or this side is a, right? So this distance is x minus a. So limit is x minus a to x plus a. And x is a function of time. So it's moving. Now we can solve it. So it's 1 by x, right? Because there is a ln x. So
That is x plus a by 2, no, sir.
which one?
Upper value.
Yes. Okay. So to get induced EMF, how to do? d phi by dt. So here you get dx by dt. So in terms of dx by dt, I will put the velocity. Solve it.
Okay. That's the magnetic field into area only, no, sir.
Yeah. So x into then a by a. Yeah. Just a constant. Area of that strip is a into dx. value of this perspective.
You have to take reciprocal of that value.
No. I think the easiest thing is to split into two terms. So ln of x plus a by 2 minus ln of x minus a by 2. So 1 by x plus a by 2 minus 1 by x minus a by 2 dx by dt, that is the velocity. So this have to simplify. So x will cancel. So numerator will become a. So mu by 2 pi is missing. Okay, is in proportional to. So you can forget the constants. So this whole thing you can forget. Even b you can forget. So it is just a divided by x square. A pound you can forget. So it's proportional to x square 1 by maybe this one. This 4x square minus a square, right? Simple. So option B. Done?
No, I don't understand.
No, this expression is clear, no? For flux. Yes or no? What is this?
That integrating magnetic field.
No,
Can you please explain it, sir?
no, this step is clear.
This stuff, okay, but previous stuff.
This one. Area of this area of the strip is how much? Dx into A, right? This length is A. And this with this dx. So area of the strip is dx into A. This is the area of the strip. This strip. Okay.
Yes, sir.
So dx into that area is a flux through this small strip. So to get the total flux, I have to integrate from limits this one. So from that we'll get this one for flux.
After ln x, if we differentiate ln, then we will get the reciprocal of that value.
No, don't differentiate that way. Just write this as ln of numerator minus ln of denominator.
Yes, sir.
Okay, so you have two terms. So this is the derivative of the first term. Okay, minus the derivative of the second term.
Okay.
Otherwise it will be difficult.
Yes, sir.
So everything will go proportional to this one and the same as this one.
Yes, sir.
Done. So I think magnetic field we have done enough. So can we move to the next one then?
Yes, sir.
We do ray optics.
Okay.
So in your folder, I put this one, chapter 9. So this is the theory part. So ray optics is, how do you remember that formula? Say for 1 by f equal to, how do you relate focal length to u and v and the refractive index?
For mirror, it is 1 by v plus 1 by u, sir. For lens, it is 1 by v minus 1 by u.
1 by u or mu by u?
Sorry, what?
It's mu by u, right? 1 by u plus mu by v equal to 1 by f.
I have to revise it, sir.
Okay.
Next is fluids only now, sir.
Which one? No, we are doing class 12, no? Then we'll do class 12. Okay, so ray of x, we do ray of x now. See, for a lens, this will have some refractive index, right? Okay, so you have to relate the focal length to U and V. So what is the relation between these three? You said no, 1 by U.
I have to revise.
Okay, 1 by V, 1 by. So this is what you said, right?
1 by V minus 1 by U.
There is mu actually. 1 by U plus V by V. And this is the direction of the instant, right? And it will go like this. So this is the positive direction, right? So U is negative, so V is positive, right? So this is the formula.
Is it for lens or?
Yeah, for lens this mu will come. For mirror it will not come. Only for lens this refractive index will come. Okay, mu is not there. Okay, fine. So mu is not there. So 1 by U plus 1 by V to the 1 by F. So I remember this minus sign by using this. The convention for sign you know, right? You have to choose the position of lens as origin and the direction of the incident right. That is the positive x-axis. Okay. So since U is this distance, from here to here. So that is on the negative, negative direction, right? So u will be negative. So to get the distance, I have to put the minus sign. Okay. This is the distance u, but actually the coordinate of this point is minus u. Or other way around, if you take the coordinate of this point as u, then this distance will be minus u. So this u is negative, and the distance should be positive, so the distance is minus u. So I remember the formula is 1 by u plus 1 by u put 1 by f. But since u is negative, I'll put minus sign u. So this is formula for lens. And what is lens maker's formula? It relates u, sorry, not u. It relates, what is lens maker's formula relate? You know this?
1 by f equal to mu2 minus mu1 by mu1 into 1 by r1 minus 1 by r2.
What does it relate? Here,
The
thing relates.
radius of the
Yeah, so it relates the radius of curvature R1, R2, and then to what? Here is FU and
mu
right?
mu
Mu and then
mu2 mu1.
the focal length, right?
Sir,
why is it-
I need some time to revise this chapter, sir.
Okay, so this thing, why is it called lens maker's formula?
Because it's essential to make use
Yeah, when you make the lens, so what are the criteria? What is the job of a lens?
to magnify the object.
Yeah, put it another way, job of the lens is to focus, right? So it's basically focal length is the property of the lens. So when you ask the person to make a lens, I just have to say make this lens with this focal length, say 20 centimeters or something. So this person, so he'll have a material. So for him, material the mu is fixed, and then he has to design R1 and R2 that he can design, right? By shaping the glass. That is his job, right? He just has to
Yes,
shape
sir.
the glass R1 and R2 such that he gets this particular value of it. So you have to know how to relate F with this R1 and R2, and also it depends on the medium also. So let's make this one as 1 by F.
Revise this chapter, sir. Remove.
Okay,
I will do some other chapter today.
another subject.
Fluids are using
Okay, so then I'll go to the theory part.
slowly, sir.
Yeah.
I forgot the concept.
So visible light is in the region 400 nanometers, 750 nanometers, and what is 1 nanometer? 10 to minus 9, right? So this is we called as light, and speed of light is 3 × 10⁸. Okay, and in this particular chapter, we are studying wave optics. The light is moving in straight line, and this is a good approximation because the wavelength of the light, which is this much, is small compared to the size of the object, which will be unknown. Okay. Path of the light is called ray, and length of rays is called B. And first, spherical mirrors. So pole of the mirror is the center of the mirror. So the mirror will be like this, or it can be like this. So the first one is a concave mirror, and second one is convex. Right? The reflecting surface is like a cave here. So the opposite one is convex. So okay, the pole of the mirror is the center point. So this is the center point, right?
Sir.
And line orientation. So since it's a spherical mirror, so the spherical mirror the way of getting spherical mirrors, you take a spherical shell and then you cut it. Okay. So since this is a part of a spherical shell, you'll have a center somewhere here. Okay, so this is a center point P, and the pole mirror symbol is P. So the radius of curvature of the mirror is this distance. So line here pole center is called the principal axis. So this straight line is the principal axis. Line on the pole mirror center and extend here on the other side. This is called principal axis, and this is the radius. Okay, this is property of a concave mirror. Parallel beam of light, parallel principal axis converge. In case of a concave mirror, and convex mirror will appear to diverge from a point in the principal axis, and that point is called focus. This is the picture. This is the concave mirror. So if you have a parallel beam of light. So what is the thing that will govern this direction of this bending? Suppose this is a line I have drawn parallel to this principal axis. So how do I get this direction? That is based on which law?
Law of reflection.
Yeah, law of refraction. So basically, suppose I draw a normal at this point, so that normal will pass through the center, right? This is a spherical surface. So if you take a circle, 2D case, tangent, you know how to draw a tangent, right? Just have to touch the circle. So normal to the point will pass through the center. What is property of a circle? This was already studied in 11th standard. Normal to any point in the circle will pass through the center. Is that correct?
Yes, sir. So
this is a circle, 2D circle. Okay. Tangent means I have to draw a line which is just touching this thing at any point. Okay, so this is tangent. Okay, and suppose at this point, if I draw a normal, this will make 90 degrees here. This property of a circle, if you extend this normal backwards, will pass through the center. This property of a circle. So similarly, in a 3D case, instead of a circle, we have a spherical shell, and we can draw a tangent plane, and the tangent plane will touch the only one point. So at that point, if you draw the normal to the plane, that normal will pass through the center. Okay. So at this point, if you draw a normal, it will pass through the center. So
yes,
the angle of incidence is this one, and angle of friction will be same as that one. So that will give me this focal point. So if you take this one, now the angle will change. It becomes smaller. Angle of incidence, so angle of reflection also smaller. This one. So all the parallel lines based on this reflection, if you draw it, it will meet at a single point, and that point is called the focus. Okay, so this for a concave lens. So similarly, convex lens, if you take this thing, if you draw a normal here, now this is the line joining this point and this one. Okay, so it will get reflected this way.
Okay, so that normal will be a perpendicular bisector between the incident and the reflected.
So the normal is here, so the reflected will go away. Here, the normal is here inside. Okay, so this reflected thing will come inside. But here, if you draw the normal, it will be outside. Okay, so the reflected will get diverged. So if you project it backwards, extend it backwards, it will meet somewhere here. So if you take a second parallel ray, that will also get diverged. If you project it backwards, so all these parallel rays, if you project it backwards, will appear to diverge from a point. So it's as if instead of having this thing, if you have a point object at this point, it's as if the light is coming from this point object placed at this focus point here. Okay. So this is a convex lens. Concave lens, the object is somewhere far away, so the whole thing will get converged here. Okay. Here it will get diverged. I can replace this whole thing by a point object at this point, focal point here. Okay. So here the rays are parallel to the principal axis. But suppose this is the principal axis, and suppose the rays are parallel rays, but they are coming at an angle with the principal axis. So here instead of meeting at the principal axis, we meet at a point away from the principal axis. So, but they meet at a single point, and this plane, if we draw a plane passing through this point which is meeting, and this focus point, that plane is called the focal plane. Okay. So here the rays are meeting at the focal point. Here it will be with the focal plane. Okay, similarly, if we take a second set of rays parallel in this direction, it will be somewhere here, but it will be the same focal plane. Okay. So parallel rays at different angles will all meet at different points, but they're the same focal plane. So this is a spherical mirror. So if you have to relate, So basically, if basically there will be a relation between the focal length, as the resisting effect is pole, and the radius of curvature of this spherical surface. So you can have an understanding. So the radius of curvature is more means R is more, the mirror will be more flat, right?
Yes, sir.
Let me just draw it. Suppose I have two mirrors like this. One is like this, another one is like this. So which one has got more radius of curvature?
First
This is
one.
R1, this is R2. Which one is more, R1 and R2?
R1.
R1. Because this is part of a bigger circle or a spherical shape. This is part of a smaller spherical shape. Okay, and which has got more focusing power? Focusing power.
Focus is R2.
Yeah. And which has got more focal length?
R1.
Yeah. So the thing is, if the job of spherical mirror is to focus, right? So if it is focusing at a small distance, then power is more. So if suppose if you have a plane mirror, okay, then radius is infinite, right?
Yes, sir.
Okay, so this will not focus. If I have a parallel beam, which is reflected back, so there is no focusing ability of this one. Okay, only when you make it curved, it will focus at a large distance. If I make it more curved, it will focus at a shorter distance. Okay, so the ability to focus at a shorter distance, that is the power of the mirror. So the power of the mirror should be inversely proportional to the focal length.
Yes, sir.
Got it? You have to understand the formula, not just know the formula. Okay, the job of the spherical mirror is to focus the incoming light rays. So if it is focusing to a shorter distance, then it means the power is more.
Okay.
Okay, so in that sense, the power of plane mirror is 0.
Yes, sir.
Okay, so the formula of the formula is equal to power is equal to 1 by 8. Okay, so this definitely there will be a relation between F and R. So if R is small means focal length also be small. And what is the relation? How is F and R related?
F equal to 2 by R.
No.
Sorry, 1 by F equal to 2 by R.
No. F and R are same,
Oh.
same dimensions, right? So F and R should be same. So if you put R by 2.
That's what I told you, sir. 1 by F equal to 2 by R.
Okay, okay. But if you put R by 2, that's a better way to understand. This is a focal length
Yeah.
and this is a radius. Okay, and that is approximately valid, and that's a good approximation then. If you could R by 2 is not strictly correct, but it's approximately correct, but it's a good approximation under what condition? When the when this parallel right ray is close to the principal axis. Suppose it's very far, then this thing is not. That is derived from the derivation of this formula. This is based on this, right? So if this parallel beam is close to this one, then this FD is approximately FT. Because when we derive this formula, we use this triangle. You remember or not? When you're deriving this formula, if you could R by 2, actually you are using that approximation that FD is approximately equal to FP. What is FP?
Distance between the focus and the pole.
Yeah, and what is FD? FD is little bit away from P. T is the point where you get by dropping the perpendicular from this point. Okay, so this distance dp is very small. If it is very small, then this f is very close to r by 2. So this t will be very small. dp will be very small if this parallel beam is close to this principal axis. Whereas we move closer and closer, this d will move closer and closer. Okay, so that ray which is close to the principal axis is called paraxial ray.
Okay.
Remember it? So this tan theta is approximately theta. So everything is related. So it's basically paraxial ray is the ray which is close to the principal axis. Okay. So for that ray, this dp is approximately 0. So in that case, f is approximately r by 2. And there's a good approximation for paraxial. So for example, just have to remember f r by 2 and this valid for paraxial. Most probably it will assume it's paraxial. Okay. You don't need this derivation. And this understanding you should have if focal length is, focal length or radius are directly related. Focal length moves, radius will also be moved. But power is inverse to focus, focal length. And similarly, you can relate U, V, and F. Mirror equation. So that is 1 by 2 plus 1 by V to the 1 by F. Here again, it's paraxial based. Actually, approximately 1 by F is a good approximation for paraxial. Same is true for lens also. Lens also, whatever formula we know, that is true for paraxial case. Because everywhere you make this approximation, you got this perpendicular, and this distance, this difference can be neglected if this ray is close to the principal axis. So you have to remove here both U and V are possible because both U and V are on the same side. Okay, so even if I take x as this way, both U and V are negative, U and F will be negative. So all U and V and F will be negative. So we have to put negative sign in everything, so that will remove and make it all positive. Okay. All right.
Show me the sign convention, sir.
The sign convention you can take it. Just a minute. See, sign convention, first you have to fix the origin, right? Origin is at the pole. Okay, so this is the origin. So x-axis is usually chosen along the direction of the incident line. Is that clear? So this is my origin, and this is the positive direction of x-axis. Right?
Okay.
Okay, now.
Okay, direction of that incident ray is taken as positive. Am I right, sir?
Yeah, that is the convention. Origin is at the pole, and the positive direction is towards the direction of the incident light. Okay, so according to this
Okay, okay.
convention, U, V, and F, these are not distances, they are coordinates. So the distance will be, distance is always positive. So the distances are minus V, minus V, minus V, and minus F. Okay, so in the formula I have 1 by U is 1 by V, with 1 by F. Since everything is negative, I have to make it positive. So I put this negative sign. Okay, so now I can cancel this negative sign. So the formula is 1 by U plus 1 by V, 1 by. Is it clear?
Yes, sir.
Okay. Formula is 1 by U plus 1 by V equal to 1 by F equal to 1 by F. And sign I will fix by knowing that the direction is, everything is negative. So to make it positive, I have to make the distance positive. So I'll put minus sign here. Now I can cancel this minus sign and get this one.
How to find the direction of the image, sir? Here it is an inverted image.
How to get the direction of?
That image. Here it is inverted, no, sir, in that
No,
diagram.
inverted doesn't matter. The distance of this image, right? It's B prime to P. Distance is this is parallel distance. You don't have to bother with.
No, no. How to draw the diagram? Basics stuffs. Inverter or erected.
This will not come in NEET, but see, if you take this point A, you just have to find the image of point A and image of point B. So image of point A, it will come here, right? A prime.
Okay.
Okay, and image of point B will come here, B prime. Or if you take the other point here, say A1, it will come here, A1 prime. And the direction of image is A to A1 to A. The direction of image is from A1 to A. Okay.
Okay, sir.
Another way to understand is, you know this formula, right? The image size by object size is the magnification. Okay, and magnification is basically the power of the lens, right? So it is fixed. So suppose I take these two images. Suppose I consider AB as one particular object, another object as A1B. Okay, so the size of AB will be this much, and size of A1B will be this much because it's smaller, right? So you know A1 is here and A is here. Once you know A1 and A, I know the direction of the image. Is that clear? Okay. This is for a mirror. And magnification is image size to object size. And this can be derived as usually. Everything is true for paraxial ray. So refraction. So reflection is the light traveling from one medium and then reflect to the same medium. Here there is no change of medium. Only the reflecting surface is there, and the medium is same. This light is in air, and after reflection it is in same medium. There is no change of medium. It's just getting reflected. Okay. But in refraction, there will be change of medium. Incident light is like this, and the reflected light is in a different medium. Okay. So here again, there are two laws, right? What is the first law? What is the first law of refraction? Don't remember?
No.
The incident, so even in the reflection, there is one more angle of incidence, angle. There is one law. There is another law which says that the incident ray, the reflected ray, these two will form a plane, right? But even the normal line is there. So if you draw the third line, even the third line will be in the same plane. Two lines will always be in the same plane, in one plane. But if you take it the normal, that also will be the plane form. So in other words, you can say the reflected ray, the incident ray, and the normal. These three lines will form a plane. Okay, this will be the case of refraction. The incident ray, the refracted ray, and the normal at the point of refraction. There are three lines now. So the three lines will form a plane. And the second law is the angle of incidence and angle of refraction as related as what? How do you relate?
Angle of incidence equal to angle of reflection.
No, that is for reflection. For refraction,
Huh.
how do you relate I and R? Are they related? If I increase I, what will happen to R? Will it increase or decrease? In the case of reflection, if I increase I, what will happen to R?
R also increases.
Because I equal to R. Okay. In the case of refraction, if I increase I, what will happen to R? That also will increase. Okay. But how is I and R related?
Snell's law of that mu times.
Yeah. So sin I by sin R is constant. That is dependent on the refractive index of the material. So N21 is refractive index of second medium with respect to the first medium. So what is second medium here? Glass, right? If I take this as glass, second medium is glass, the first medium is air. So refractive index of second medium with respect to first medium is sin A by sin R, and refractive index of glass is more, right? So this is greater than 1. So numerator is greater. So sin A is greater than sin R. In the first quadrant, sin A is greater than sin R means angle is greater than.
So N21 means N2 minus N1 or N2 by N1.
N2 by N1.
Okay.
In the first quadrant, yeah, so yeah, so in the first quadrant, as angle increases, say this angle theta, what will happen to sin theta? Will it increase or decrease? Angle is increasing. So sin theta will increase or decrease?
Increase.
Okay, so 0 to 90 degrees is like this, right? This is 90. So it will increase. So here, N21 is greater than 1. So sin A is greater than sin R. Does that mean I is greater than R? N21 is
Yes, sir.
sin I by sin R, and this is greater than 1, right?
Yes, sir.
So sin A is greater than sin R, that means I is greater than R.
Yes, sir.
Okay, so in the denser medium, which is glass, the angle is less, so that means that the ray will move towards the normal. Because
Yes, sir.
angle is measured from the normal. Since the angle is less, so the incident ray is projected in the forward direction would be like this. So when it moves in the denser medium, the reflected ray, the refracted ray will move towards the normal. Okay, so this fact, can you relate to the fact? So what is the velocity of light in air and velocity of light in glass? How is it related? Which one is more? Velocity of light in air is more, or velocity of light in glass is more?
Air only more, sir.
Yeah. So
If it is denser means the speed will decrease.
yeah. So that can be related to the fact that the angle is lesser. So if it is moving slower means it has to travel a shorter distance. Suppose if the light was moving along this direction, then it will travel a larger distance in glass, right?
Yes, sir.
Okay. Suppose it's
Longer
moving,
distance.
yeah. Suppose it's moving towards this normal then the distance you travel is shorter. Okay. Since the speed is decreasing, it has to travel a shorter distance to come out of this boundary at the same time.
Okay.
Okay, and that is related to the fact of law of conservation of energy.
Okay, sir.
You take any cross section, whatever energy is flowing across this area, that should be same at any given. That should be same at either instant of time when it is crossing it. Okay. Similarly, if I take a cross section here and the cross section here, the amount of energy that is crossing this area should be same amount of energy. Okay. So here, since this is taking speed is smaller, so it will take a shorter distance to transfer the same amount of energy, because whatever energy is entering this part, okay, should come out of this point at the same amount of time. Okay, so suppose if it's starting like this, okay, then the amount of energy coming out of this point will be lesser because you've taken longer time for the energy to travel. Okay, this I'm saying just to remember, whenever the speed is decreasing means it will take a shorter path. The shorter path means we have to move towards the normal. Because in a triangle, this path is shorter compared to this path. Okay, as you move closer to the normal, the path becomes shorter. Okay.
Yes.
So here, this is here, this is glass, and again it's coming out. So when it is entering a denser medium, the speed is decreasing, so it will take a shorter path. So it will move towards the normal. So this is a short path, and when it's coming out, now it's going to move faster, right? So it can travel a larger distance. It's moving away from the normal. Because if I project this refracted ray, this forward direction will be here. So it's moving away from the normal. Okay. So this R2 will be same as I2. Sorry, I1. Okay. This R1 and I2 will be same. Because it's a rectangular glass slab. So these two sides are parallel. Okay. So when these two sides are parallel, this normal is parallel to this normal. So these two are parallel lines. And there's a single line which is passing through these two parallel lines. So this angle and this angle should be same.
1 minute, right, sir? I can't understand slowly.
This is a rectangular slab. It's not true for prism. It's a rectangular glass slab. The rectangular glass slab means this and this are parallel, right? This and this are also parallel. That doesn't matter, okay? Because the light is getting reflected at this interface, and the interface this interface. Okay, you have to consider these two interfaces and they are parallel because it's a rectangular slab. Okay. And this is normal at this point, this is normal at this point. So these two normals are parallel. So the normal is making 90 degrees with this line, and this normal is making 90 degrees with this line, and these two lines are parallel. So the normals are parallel.
Yes, sir.
Okay, so then the normals are parallel, and this is same line which is cutting two parallel lines. So these two angles are 180 angles. Right? So I2 is same as R1. You have two parallel lines and the line cutting them. These are called alternate angles, right? They'll be equal.
Okay. Yes, sir. Yes, sir.
Okay. So I2 is same as R1. So and R2 is same as I2, I1. Can you prove that? How do you prove that? By using Snell's law.
Snell's law.
Yeah. You have to apply Snell's law of this interface and you have to apply Snell's law of this interface. So if you apply Snell's law of this interface, you get this is medium 2, right? So sin I by sin R equal to N2 by N1. here you will get sine I2 by sine R2 equal to N2 by N1 by N2. Okay, here the first medium is 1 and the second medium is 2. Here the first medium is 2, second medium is 1. Okay, so same steps are applied here and here. So from that you get R21, I2, I2, I1 Okay, so Snell's the first interface will get this one. Snell's the second interface will get this one. And this and this are reciprocals. Okay, so this and this reciprocal should be same. And R1 and I2 are same. So from that I'll get I1 equal to R2. So image and trace parallel to the instrument. So since R2 is same as I1, these two lines are parallel. So these two lines are also parallel. Because I1 is the angle made by this with the normal, and R2 is the angle made by with the same normal. So this final emergent light ray and this incident ray both are parallel. And this is true only for a rectangular slab, because these two lines has to be parallel. Everything is valid, whatever we discussed. And we can get the exact value of the shift. Okay, so this shift, on what parameters it will be dependent?
Medium.
Yeah, medium is one thing. After that, so suppose this length, okay, will it depend on this length? It's actually proportional to this length. Because suppose if this length is 4, so this point, it have been here, right? Okay, so that itself will give you a more shift. So the lateral shift we can actually, so just not derive it. Now there means that. Okay, you can the lateral shift is this distance, and you have to drop a perpendicular from here to here. Okay, and or yeah, this is the distance. Right. So this distance is, what is this distance from here to here? Suppose this distance is say B. Okay, so what is this distance?
BR1.
No, triangle, right? Right angle triangle. Cos R1 is D by this length, right? So this is B by cos.
Where is that D, sir?
This is B from here to here.
Okay.
Okay, so this is B and this hypotenuse. So this is B by cos R1.
I see.
Looks like it's not there in this list. Okay.
They might have deleted it, but it is there for NEET syllabus, sir. Not for CBSE, but
In the gas lab is fixed. So this length is say fixed. So let me call this as B. So this will be B by cos R1. Okay, and again I can construct one more triangle like this. So now I can use this 90 degrees. So if we take what is this angle? I1 minus R1, right? This whole thing is I1.
yes, sir.
Okay, so this is I1 minus R1. So if we take tan of I1 minus R1, that will be the lateral shift. We call it D. divide. So I should not take time. I should take sine. And it will be opposite by hypotenuse. E divided by the hypotenuse, that is E by cos r. So E is B into cos r1 divided by sine of I1 minus R1. Okay, suppose this medium is same. So this is also here, then I1 is same as R1. So this is made a mistake here. This is the way we are right. 1 by B. Okay, because if I these two mediums are same, then I1 is same as R1. So D should be 0. Alright. The lateral shift B is B into sine of I1 minus R1 divided by cos of R1.
Yes, sir.
If this medium is also A, then it means that I1 is same as R1. If you put I1 equal to R1, this is sine 0. Okay. So then D will be 0. That makes sense, right?
Yes, sir. That makes sense. Yes, sir. Shift.
So the thing is, if this distance is more, means then the lateral shift will more. So distance, the amount of shift depends on this size B. So real depth versus apparent depth. That's again based on this same thing. Okay. So the interesting thing here is, suppose you look directly from the top, then also it will appear as if the thing is giving diverge from this point. If you observe from an angle, then also it will observe as if the object is here. So the height of this shift rho prime is same whether I observe from directly above or an angle. Okay, so this so the real depth is this much, apparent depth is this much. Real depth is switched to. So refractive index of the real depth is apparent depth, and real depth is more, right? It's greater than 1. So n1 2, so it should be n to 1. This is the second medium. So, okay, depends on what is the meaning of this n1 2. This is actually a refractive index second medium with respect to first medium. So maybe the meaning as so n to 1 is refractive second medium with respect to first medium. That's the convention of used. This is refractive index of first medium, so it should be n. So here is the second medium, and here is the first medium. The second medium is denser medium. Here it is water. Water is also denser. So n to 1 is real depth by apparent. Real depth is more. This is greater than 1. Is this clear? Okay. The mic is off.
1 minute, sir. Let me see the diagram first.
Okay. See, the light is coming from here, right? So if we take this as first medium and this as second medium, then refracting to the first medium, this is second medium. Okay, that's fine. This is n1 to 1. This is first medium because light is going from here to outside. So this outside air is second medium. this water is first medium. Okay, it's N12 only. And real depth is more, apparent depth is smaller. So real depth by apparent depth is greater than 1. So N12 is the first medium and it is greater than 1. Okay. So remember, like the real depth by apparent depth is greater than 1. The refracting, so they should be refracting the density medium. Okay, so refracting the density medium equal to real depth by apparent depth. Got it?
How did you get that apparent depth diagram?
No, this it's not required. See, again, it's the Snell's law only. See, this is density medium, right? So when it goes to error medium, it will move away from normal.
Oh, that I understand, sir.
So
After that,
once it goes away from normal, you project it backwards. So it will meet at a shorter depth. See, the basic idea is, suppose if I don't have this water, okay, and I place an object here, O prime. Okay, second case, I have this object with water and the object is here. So those two situations are equivalent. Let me explain this one. So this is the first case where you have water and you are in air. Okay, in the second situation, instead of having water and just have air, okay, and but I have an object here, okay, and you are observing from here. Okay, so these two situations are equivalent. So because from here, the light will come out like this. Okay, but in the first case, the light is coming from here, it's bending and coming out like this. So for eye, these two situations are not different. So it's as if for the eye, there's an object at here, at O prime. Getting the idea?
the object is in air or sir, in the green color.
No, in the first case, object is in water, okay? Here.
Okay.
So when it's in water, it goes here, it bends and comes out, right? So if you project it backwards, it's as if the light is coming from it. Second case, you assume that there is no water, it's fully air, but the object I'm placing at O prime. Okay, so the light rays will go like this and come out like this. So this part of the light ray here and here, both are same.
Yes, sir.
So for the eye, it cannot make a difference between this and this. So it will assume as if the object is here.
Yes, sir.
Okay, so that's why it's as if the object is kept here. So the object is at a shorter depth. I will assume that the object, the light rays are coming from this point. Actually, the light rays are coming from here. It's bending and coming here. But since I will not sense that it's getting bent, assume that that's it. It's under the illusion that the light is coming from here. Got it? No.
Yes, sir.
Same thing happens for this first case of this convex mirror. Okay, so this is equivalent to, suppose I have an object here. Okay, here actually the object is an infinity. It's a whatever object is there, parallel beams are coming from there. So instead of that, if I have an object here, okay, this will produce the same light rays. Got it? No? So these two light rays I can get either by having object for infinity, it comes and gets reflected and I get it. Other way of getting this light rays is instead of this mirror and object here, I can place the object here and the light is coming out of the object will look like this. So the eye will assume as if the object is present here. That way this becomes a virtual object, or you can say virtual image. It's as if the object is kept here. Okay, so that's what happens in plane mirror also. Suppose this is plane mirror and you're standing here. Okay, what is actually happening is light is from here, it's going and reflecting back, right? But suppose I instead of that, it is getting reflected. So this light ray will match with this light ray. So instead of this mirror, if I have an object like this, say some clone of myself here, both the effects are same. So it's as if someone is there here. So that's how you see your face here. Okay, instead of having yourself and the mirror, suppose I have a clone of yourself here. Okay, this is the mirror position at this distance. Both the effects are same as far as eye is concerned. So it's as if someone is there inside. That's your face. That's how you see. That's how you see yourself in the mirror. And suppose I move farther away. Okay, this image will also move farther away.
Yes, sir.
Okay, so since okay, it's not complicated. So this is the basic idea. So whenever we have virtual object, it's as if nothing is there, but there is an object sitting, and the light is coming directly from the object. So for an eye, it will not make a difference whether the light is coming from here, you're getting reflected and reaching you, or it's getting straight away from an object, virtual object. So for an eye, it will appear as if the thing is coming from an object located here.
Yes, sir.
So the effect in the eye by this light ray, which is going here and going here, and the light ray which is coming straight here, both are same. Because the eye is going to sense only these lights. Okay, so the eye is our human illusion is such that it will think as if the object is here. Okay. So this is concept of total internal reflection. So when a light ray is traveling from examined parallel medium, so 2 is this parallel medium. Okay, so into 1, is it less than 1 or greater than 1? Into 1, is it less than 1 or greater than 1?
Lesser than 1.
Lesser than 1, because it's refractive index of second medium with respect to first. First is youngster. Or another way to is to say that it's ratio of the second medium divided by ratio of the first medium, right? No, it's the other way around. Ratio of the first medium by ratio of the second medium. So it's ratio of light is more than the second medium. So it's less than 1. And it's sine by sine of, so I is the first medium. So here I is less than R, or angle of refraction is greater, right? So the refracted ray will move away from normal because it's going faster. So it can travel a larger distance in the same amount of time. So we'll try to cover larger distance. So that it can be done by away from normal. Is that clear?
Sure.
Okay, so R is greater than I. So if we keep increasing R, that will happen if I take this light ray. This light ray, the angle of incidence is more compared to this one. Here, for this particular light ray, the angle of incidence is 0. Okay, if you keep moving away and away, the angle of incidence will increase. Right? Simple geometry.
Yes, sir.
Because if you take this line and take it move far away, so this angle will keep on increasing. So it will increase, and as this I increases, R will also increase, and R angle of refraction cannot increase by beyond 90. At a particular point, it will become 90, but IC will be still less than 90. Because here I is less than R, because R is moving away from normal. So this particular point is a critical point. After that, if I try still if I increase I, there won't be any refraction. It will be fully reflection. This it's called total because all the light rays are getting reflected. See here in this case, when it's getting reflected, some amount of light will get reflected. If you take a even a plain glass, if you go and stand in front of it, you can still see your face, but it will be somewhat dim. The reason why it is dim is good amount of light is large fraction of light is getting refracted. Only small fraction of light is getting. Suppose this is 100, 90 will get refracted, and 20 will get or 10 will get reflected. So the image of your reflected image will be done. But if it thing is total internal reflection, then this reflection, all the light will get reflected. That's why it's called total reflection. Total internal reflection. Okay, total in the sense that all the incident light is getting reflected. Refraction is zero. Alright.
If we move from rarer to denser medium, also some of the rays will be reflected, sir.
Yes.
I mean, partially reflected.
Yeah.
Okay, it holds true for if we move from rarer to denser medium.
Always see here also, moving from rarer to denser is getting refracted. Here there is no question of total reflection, but still small amount of light will get reflected. Okay, maybe 2% or something. Okay.
Yes, sir.
But when you're moving from denser to rarer also, always reflection will be there, some small amount. Okay. But when you go beyond this point of critical angle, then the refraction is not possible. So it will be total no. So it is, at this point, he has a perfect mirror. Okay, so this object kept at a, suppose my eye location is here, I can see the object. If my eye location is here, then no light from A will reach this eye at this location. So I won't be able to see this object. If my eye location is here, some light has to reach from here to here, right? So that's not possible because if the light which goes here will go inside one. Okay, no light will reach this point. Okay, so the amount of region where this object will be visible is up to this point.
But what if I'm in the water?
In the water, you say this object, right?
Ah, yes, sir. Okay.
You don't have to go to this interface. Okay, fine. So I think now we can solve some problems. We can do it in next class. Yeah, as far as theory is concerned,
still we have so much of theory left now, sir.
No, this is okay.
It's
this is
huge lesson.
Yeah, this is like plain rectangular this thing, and then now we are moved to prism.
And refraction at spherical surface.
Prism is not there. Prism is there.
Prism is there, sir. 20 question also related to prism.
Okay. There and it's there. Oh, prism is there.
The refraction and spherical surface and lens in contact, those stuffs.
Yeah. Just now we come to rectangular surface. After there will be prism. After that will be lens.
Oh, okay.
So see the difference is here we have two faces are parallel, right? That's why this thing is just a lateral shift. Or suppose they are not parallel, again the condition is same Snell. So since it is not parallel, we will get diagram. Again, This again, all these things are valid. Sin I by sin R, R1 equal to mu2 with respect to that. So similarly, here also we can apply that. So here when it comes to this medium, it will move away from normal. So I and B. So in the case of the rectangular slab, I and E will be same. Okay, but here it's not because these two normals are not parallel. It's completely different thing. So the thing is, basically this bending. Suppose this AC is not there, it's bending from here to here, right? Because the second interface it is bending still more. Got it?
No.
Suppose if there's only one interface. So now this is the incident light and this is the refracted light, right? So now the second interface, again it is getting bent like this. So compared to its initial this thing, suppose I just consider this interface, the angle of deviation is from here to here, right? Okay, but because of this second one, it's getting still deviate further. Got it? So if we take these two, this is the incident light and this is the refracted light. So the amount of deviation is this much, right? Yes or no? This much is the deflection. This is the incident light and this is the refracted light, right? Just this interface, first interface. Okay? Yes or no?
Yes, sir.
Uh,
No, wait, sir.
okay, now this thing is, with respect to this refracted ray, still is getting further deflect. So this is the total deflection. That's
Here at QR is refracted ray, sir.
If you consider this interface, this is refracted ray. If you consider this interface, this is refracted. Or what name you give, it's not different. That doesn't matter. What is happening?
No, I'm asking QR is refracted ray or what?
What do you want to call it? What do you want to call it? That doesn't matter, right? It is a okay. You can say it's refracted ray. What about RS?
RS also refracted.
At this interface, second interface. Okay. If you want to give a different name, if you want to give a different name, you can say it's an emergent ray. Okay. Basically, there are three rays: 1, 2, and 3. What I'm saying is between the angle between 1 and 2. Okay, and it's still getting increased between the angle between 1 and 3. The angle between 1 and 2 is this much angle. Angle between 1 and 3 is it's getting still further deflected. How to put it another way? The total deflection is delta. Delta will be greater than the first deflection is I minus R1. Okay,
what is deflection, sir? I forgot.
This is incident ray, right? And this is the refracted ray. So this much is the amount of deflection.
Yeah. Can you please draw normal to that surface, sir? First interface.
See, this incident light would have gone straight like this, no? If this interface was not there, but because of the interface, it has gone like this. Yes or no?
Okay, Q1 is normal.
Yeah.
Fine. Yes, sir. Yes, sir.
Okay, so this slide would have gone straight like this, but because this interface it has gone. So this is the amount of deflection, right?
Yes, sir.
Okay, but as interface again is getting deflected. So this is the second deflection. Okay, so this total deflection delta. Delta is the deflection between this initial incident light and this final image on top. This is the total deflection, right? Delta. What happens is delta is this deflection. This deflection is how much? I minus R1.
Yes, sir.
And this deflection is, second deflection is E minus R2. Same logic. This is E minus R2. This whole angle is E, right? Opposite angle. So this angle is E minus R2. The same as this angle.
Where is that? The delta, sir. Second one. I can't see it.
This is the delta, right? Second delta. Sorry.
Huh?
This is the first ray. This is the second ray. This much is the deviation. This is delta 2. Here is delta 1. This is delta 2. And delta 2 is E minus R2. This is same as this angle, right? Vertically opposite. Okay, this is simple geometry. So delta will come out to be, I mean, this is all. Delta is I minus plus E minus R2. Okay, these things are all there in NCERT. This is all very simple geometry. Okay, you just read this one. Okay.
Okay.
This total deflection is the deflection at this interface, that is I minus R1, and the deflection at this interface, that is E minus R2. Again, you can relate R1 plus R2 equal to by this angle. Property of a triangle. Can relate R1 and R2 to angle E. Angle E is the angle of the prism. Angle of the prism is the angle between the two refracting surfaces. That's not angle between this and this, because the two refracting surfaces are these two. So you will take the angle between the two refracting surfaces. That is the angle of the prism. This angle does not matter. Whatever B and C is, does not affect these things. Very dependent on this angle. This R1, this angle is how much? 90 minus R1. This angle is 90 minus R2. Somebody will get R1 plus R2 equal to B. Okay, close now.
Yes, sir.
Go through this NCERT.
Yes, sir.
Okay.
Bye, sir.